Aurel from Investec. So we are a firm in R&D of crypto protocol.
Yeah,
You heard that? Yeah. So, yeah, thanks. There we go. So what is a HawkPack? So this is about search protected by cryptography, right? Like privacy-preserving search. Yep. There we go. So the problem statement is we want to do a similarity search, like look for similar images or documents. So it's a very common problem in AI. It's known as embeddings. So basically, we have a vector of numbers, and we want to find like the most similar one or the top 10 most similar ones. Except that the database and the queries are both private. And what it means to be private, there are variations, depends on your application, what you want to protect from who. Right? We'll see it's very flexible. That's why it's written that way. And the database is very large, so we're interested in scalability, and it's also high-dimensional. And the high-dimensional, as we'll see, that excludes a lot of options. So our baseline is the exhaustive search. So you have a new query come in, scan the database, do all the comparison, like between vectors, right? Like calculate a distance, like an Euclidean distance, a Hamming distance, cosine similarity. Then you have all these distances, you compare them to find the minimum. Right? And I always insist on you calculate distances, then you have an object which is a distance, and you can compare distances to find which one is the smallest. Right? So that's a map reduce. So that is very expensive. That's the big problem with that, obviously. All right, does anyone have any idea how to accelerate this? I already showed this slide. So it's funny, every engineer who works on this has to go through the 5 stages of grief, you know, where first you want to do LSH, right, like a locality sensitive hash, something like this, right? Or you want to do clustering, like you're going to train k-means, find 100 clusters, and then you say, oh, I'm going to look only in the best cluster for my query, and then it's 100 times faster. Or only the top 10 clusters, and so on. You can try to redefine the distance to be faster, because I said it's going to be high-dimensional, so the distance is expensive to compute. So you could say, I'm going to make a much cheaper distance approximation, reject everything that is like really far away, and then look only at the subset, right? Okay, so. And I can do layers on that, and then I'm faster. Still a linear time, but faster. You can go for something like Bloom filters and all this family of data structures, right, that are approximations based on hash functions, basically. And there's a really interesting family of constructions that are based on error-correcting codes, like fuzzy commitments. And that is really cool techniques. But we'll see that. So fuzzy commitment is like an error-correcting code, and you leave out part of it. So if the query is close enough to be correctable by the code, so you correct it, you find the code, and the database contains only a hash or a digest of it. So you try to correct, and if you find the same digest, you know that you have a match. So you can construct a search engine that way. So all those techniques, when you are in high-dimensional data, it doesn't really work. Like, you get a small speed up, and accuracy goes down really fast. Like, it's very hard to do like a 99%, 99.9 recall, right? And speed up is going to be like 3x, 10x at best, but there's a very bad trade-off of accuracy and speed. Like that's high dimensionality. That's just the curse of dimensionality. And you have to make assumptions, right? If you're training a clustering algorithm or something. We don't want to make assumptions about the data. Actually, we don't know of any. So we have one application for this. And there we make no assumption. Like, the data is like random vectors from our point of view. And some of them, they have like a strange concept of privacy. Right? Like the error correcting codes, for instance. It's a little strange, right? Because you're leaking like part of this code. Right? Yeah, like it's not like in cryptography where you leak 0 bits. Here you leak a number of bits that's just enough to reconstruct, and that depends on the entropy that comes with the data, right? Like the data is trying to encrypt itself in a way that's you have very strange trade-offs. And if you want more accuracy, you have to leak more. So yeah. Okay, so what we came up with to do that is to use an algorithm which is called HNSW. So that's very famous in the AI world. That's how image search in general work, or the RAG pipeline with your LLM, right? That uses this. If you use Quadrant, Chroma, Pipecone. Yes. What does it stand for? Hierarchical Navigable Small World. So small world, that means a graph, a network. Navigable, that means going to work really well to walk through it. And hierarchical, so already with the network, with a graph, you see that we're going to have a logarithmic speed up somehow, right? And hierarchical, it's actually multiple graphs. So you have a small graph, which is coarse. So to first find some locations in the larger graph of the next layer, and the bottom layer has everything. But you start from a good point in the bottom layer. So that's the hierarchical part. Yeah, so then the search is going to look like, we'll make an example, that's maybe better. Yeah, this search is you start at an entry point and you maintain a set of candidates and you try to improve your candidates. So you look at the next candidate, look at the neighbors, pick like what is an improvement, so that opens up new paths, and you update your working set of candidates that way. So the extreme, if your working set is just size 1, it's like a walk, right, through the graph, but you're maintaining more than one, maintain maybe 100 candidates at a time, and you improve them all at once, right? So it's like 100 ants walking over the graph. So we get a logarithmic scaling, which is way better than all the others, starting at a certain scale. So in the tens or hundreds of thousands database size and up, millions and so on, it becomes very, very interesting. The logarithmic scaling kicks in really fast. Like once, like the difference between 100,000 and 100 million, that's like, almost the same. Like it's a small factor. And it works in high dimension. It has no assumptions about data. So it works on random vectors. you can sample random bits, and it's still going to work, right? It's going to pick up a small signal from neighbors to neighbors, and yeah. So that's very, very useful. So hawk pack. So hawk is the bird, who represents the search, the accuracy, and the pack that represents the decentralization. So what we want to do is to connect this algorithm to privacy-preserving techniques like homomorphic encryption or MPC. So the MPC network is the pack. And we have two implementations. One is in Rust, and that's where you're going to plug in the crypto. So this Rust library is going to drive your cryptographic protocol, right? So in the application, you have to choose how you're going to do MPC, what technique you use, and Hawkpack is going to tell you what to do, like the sequence of steps. And we have a Python implementation because you have a lot of parameters in there, and you want to also be confident about what accuracy you get, and you want to predict your performance. So we have a Python implementation with a lot of counters and metrics, and it's easier to hack with it. We have notebooks and things like that in there. So that's what I will explain. So the beauty of HNSW is how little assumptions it makes. So we don't care about vectors. We don't care about distances. We only care about this. We have vector identifiers, okay? Just ID. Identifier A and B and C. And I want to know from base C, is A or B the closest, right? And that translates into the decision of going through a path or another, right? So the result of that is a Boolean. It's not a number. So let's say you make a database where that is distributed, right? Like it's a secret shared, for instance, or it's homomorphically encrypted. And the algorithm is going to ask this question. Okay, this ID, which one is best? And then you run the MPC, output a Boolean, so reveal the Boolean, and then the algorithm can take the next decision. So how exactly you protect the vector and how exactly you compute it, that depends on the application, that depends who are the actors and the privacy model. So, yeah. And we have explored both, maybe AFHE, it's just HE, so it's, and MPC as well. So ultimately, we preferred MPC because it was faster. Or even with homomorphic encryption, you're going to have an MPC to decrypt, right? So it's but doing a full MPC, it has the advantages that when you calculate distances, in some MPC protocols, you can do an inner product, which is very fast, with like the inner product of dimension however many thousands counts as one multiplication in the MPC rounds. So okay, challenges. We do have some leakage, so we leak the path of the search queries through the graph, right? Because we reveal those Boolean, go left or go right, and whatever system it is that does the search, it's going to see these Booleans and the path through the graph. So that can be acceptable. It's okay. That's like quite removed from the content if you're trying to protect only the content of the vectors. But then you can add layers of security on top, like a TEE, run the algorithm itself in a TEE. So only the TEE sees the path. Or we're also working on this. We're thinking how to do something with oblivious retrieval, like a cryptographic protection of this path as well. And of course, that adds a big cost on top of it. Right? Can still be faster than the exhaustive search, but you're going to have HNSW plus oblivious retrieval of the shares or ciphertext, and then the MPC computation on the ciphertext. Still end up faster, but of course that's like not very easy to do. And how you can do that, that depends on your application, right? Like who is the oblivious server and client and so on. So, okay, the other problem is that you have a high latency with that. So if you do the exhaustive search, yeah, it's very expensive, but in principle, you can put 10,000 processors on it in parallel, and it's low latency, right? Like in the GPU processors. And in HNSW, you do have a walk, so that's a sequence, right? So that gives you some latency. So the total computation is much smaller, but it's more sequential. And we can parallelize a lot of it. So, but it's hard. It's not as trivial as map reduce, right? You have to really have an implementation strategy in it to decide what you can do in parallel, in advance. Some of it you can do speculatively. And I have a graph about this. You can also do in parallel a speculation. Some of the things you computed are not going to be used after you know the decisions from like the other threads, but you still like way smaller latency. So yeah, so that's the main thing that we're working on, right? Like that's how to parallelize this. I wanted to show some. So this, I believe, I already explained. So if you have a similarity search problem, that's your process. So define the privacy and the crypto protocol for it. You need this operation, as I said. Then what you can do is count how many operations or how many times we're going to call it, right? So that you can predict your performance. And the other side of the coin is you want to measure the accuracy. So if you're only interested in the top 1 result or the top 10, or what is your metric? And then you're going to tune the parameters. So there is a whole family of parameters that control the connectivity of the graph and how broad the search is. And of course, that's a performance accuracy trade-off. Let me just find the pictures. So that's the kind of scalability that you can get. So with the database size increasing, and you see very clearly the logarithmic scaling, and when you multiply this by 100 to the right, you're going to be very happy that it stays flat. And you have those two operations, right? Like how many distances. You have big vectors in high dimension. You have to compute the distance. You have an encrypted distance now in your hand. You have 2 of them. So from the 3 vectors ABC, that's the AB and AC and BC. And then you have to compare them, right? And the comparison is actually, in our case, it's like way more expensive because you have to do a binary decomposition, right? You have a ripple carry adder inside to do the comparison, and that's like way slower than the giant inner product for some reason. So you count those, multiply by how long it takes, and that's your prediction. Yes?
Can we define sort of the operation here? Is this like, as you sort of said in MPC, maybe that's like one operation of the whole vector?
Yeah, you have. two vectors, and you calculate the distance, like Euclidean distance, something.
Like, is this like one MPC round? So do I need to have 25,000 MPC rounds?
Yeah.
And so what's roughly my latency then there? Are we talking minutes? Or just ballpark figures?
Yeah. Those are very large parameters for very high accuracy. If you can probably do a lot smaller, and that's without parallelism. Yeah, so that's the total. So you might do maybe, let's say, 100 operations in parallel, right? So you're doing some 100 things in parallel and 100 times in a sequence, right? And that's like 10,000 operations. But that's the order of magnitude.
I'm just asking because it's a very interesting problem. I thought about in
Yeah.
the past, and so I'm very curious to see where the advances go.
Yeah, so you do have this high latency. So yeah, multiply by the number of rounds, multiply by milliseconds. It's really intended for like in data center MPC, right? That's not like a worldwide MPC with hundreds of milliseconds of latency, right? That's like a millisecond latency between the servers. Yeah, and again, that's the high end of the range, right? What else do I want to show? Another thing you might want to measure, again, on your data, right? That's like totally dependent on your data, but that you can observe how deep the search goes into the graph, right? So it starts at an entry point, jumps to the next neighbor, and next, right? Until it finds some kind of local minima. So it has a working set, then it's full, and then it goes, it unrolls, so it kind of rolls back to the next best candidate. And so we're back at a lower depth, right? And then walk into another direction. Right? So you can observe this. So that's what the Python implementation does, right? Like keeps track of all those counters and so on. Then you can grab them, and then you can use that to optimize your latency and parallelism and the parameters of the algorithm. Anything else? Yeah, that's the justification for the parallelism. So what you see here, that's so towards the right, that's like time. That's the progress of the search. And this is the frequency of actually improving your set of candidates, right? So at first it's empty, so okay, you just add. And then it's kind of random, right? It's whatever is the entry point. So that's what you have in your working set at the beginning. Then you find better vectors and better and better and better. And once you found them, it becomes very unlikely that you continue improving, right? So you have a quite fast convergence like this. And that means after this phase, right, where once you're here in this search process, that means what you're going to do, you always look at, you are somewhere in the graph, you have all these neighbors and they're all bad, right? Kind of. So you just go to the, maybe sometimes one of them is an improvement and you go that way. But that means your working set doesn't change that much anymore. That means you can do speculative computation, right, in parallel, and it's going to work. Like you're not going to waste a lot of speculative computation because it is invalidated not very often. That's what this is trying to show. Anyway. Yeah, I think that's time's is up.
Thank you. Anyone else have any questions? We have time for a short question or two. A little faster.
Thank you. Thanks for your presentation. Is there any reason you haven't used the ORAMs for, let's say, obfuscating the access path of the queries? Have you looked into that approach?
Yeah, that's an axis for us. That's next, but we're still working on the main one already, and that would be the next phase to perfection, right? Like to perfect privacy. Yeah, but the difficulty is like you think of ORAM is the setup, like who is the client and who is the server, right? And that doesn't match exactly. We have to invent something. For our particular application, and for your application, maybe it's you have a client server like this or not. And so, yeah.
Okay, thank you.
Hi, thanks for the talk also. And I think on slide 9 you showed us your GitHub repositories. I checked that one out. But you said there's the cryptography, the MPC and the HE part is not in there, right? So is there the cryptography that you're using for your benchmark, is there also a public GitHub repository that that I could check out? And if not, which MPC protocols and HE protocols, I say, you're using for your benchmarks?
Yes, so we have a proprietary application, like with an MPC, a custom proprietary project. So far, it will be released, I think, maybe next year or whatever. There will be announcements. So that's without the crypto part. You have a trait, an interface in Rust, and that's where you plug it. I don't think we have an example. We have plain text examples. Otherwise, yeah.
Okay, thanks.
We have also like database integrations with Postgres to store the graph. And, yeah.
Okay, thank you.
Thank you.